Okay, Chapter 1. We know the list of 5 things we're going to check out, see what we can see with our naked eye. So, what can you see just standing out there? You may not realize that you're on a sphere that's moving. It doesn't feel like we're moving, right? It doesn't feel like we're moving. You'd be surprised how early people figured out that we were actually not on a flat Earth, but a spherical Earth. People knew that a long time ago. It's pretty easy to see, so I'm not sure why that flat Earth idea comes around. And you can see different things from the northern hemisphere, because you see up there, and from the southern hemisphere, but that's Chapter 2. I mean, we're stepping out. What can you see? So really pause and think, and then I'll list it. You've got the book. So here we are. With it. It's running like that now, but there it is. All right. Sorry. Oh, you see Orion? Ignore that reflection. Sorry about that. Low production value. All right. Now, what's interesting is that around the globe, people often saw a hunter. Why? Because we're humans. We see humans, right? We see the body, right? So I draw this. People saw humans who saw the waist, the belt, shoulders, Beetlejuice. We thought it was going to blow up, but no, it doesn't seem like it's going to, but it's going to at some point. Beetlejuice, Rigel, Arabic, a lot of Arabic names that then got kind of messed up. I think that means foot, and then I think that one got messed up in translation into different, lots of languages. Sirius, the dog star, Procyon. You don't have to memorize that right now, but the winter triangle. There are patterns, right? You can make up whatever pattern. You can draw a dog. You can draw whatever you want. You can make up this. Look, there's something. You can make that up. Name it. Name it after you. Make up a story. That's all they are. With due respect, stories are great, right? They tell about us, how we're thinking. But people often saw a hunter, one way or another. Different names, not always Orion. There it is, a sword. Oh, there's some cool stuff. I'm gonna see. But do you notice? What can you see with your naked eye? Just right there. This is a photo from one of my students. Right? Can you tell that this one's brighter than that one? And then you might go, this one's even less bright. Ooh, that one's really less bright. Less bright. So one thing you can do is you can draw your picture. Maybe you'll draw a bigger dot just to represent looking brighter, right? And a smaller dot for now. Okay, let's take a look. Sure enough. You see, with stars, I want to list 5 things about stars, glowing dots, that you can see, and 5 that you can't. And if you think about it, this will make sense. You've just been busy doing other things. But we just saw, and you can see in the night sky, that how bright a star appears is something you can tell. You could, with your friend, that one's really bright and that one's dim. You'd agree with your friends. We're going to check that out now in a second. We rank the brightness. I'll explain that in a second. And we call it apparent magnitude. Apparent for visual, naked eye, right? Apparent, how it appears. Magnitude is a ranking, like first place, second place, third. I'll tell you in a second. And we use lowercase. Details matter, not uppercase. That means something else. It means absolute magnitude. It's ranking something else. And I'm not going to get into that too much, but apparent magnitude. How bright it looks. Let's take a look. All right. I think this is kind of cool. What are we doing? Yep. Now, if I turn off all the lights in our new planetarium, be able to, you won't see that. You won't see that. You won't see these because they're not glowing. But you see stars in the darkness of the night because they are glowing, right? Which one appears brighter to you? You can tell, right? You can tell. But there's some really interesting questions that come up here. Right? There's some really interesting questions that come up. This, however, is an object that doesn't glow. It reflects the light though, doesn't it? But if I turn off the light, you can't see this. You will see these glowing dots. We'll talk about that in a bit. Okay. So how can we just start making sense of it? That's what people do. Because being a scientist is part of being human, like a musician, and so on. And this is how we're going to rock this. Guys, gals. I guess guys means gals too. Here we go. Let's take a look at some details, shall we? Is that good? All right, maybe. Yeah, I think we got it all. All right. You can see it. So here's what we're going to do. We're going to look up at a bunch of dots in the sky. And yeah, just a bunch of dots. And some will appear brighter, some will appear dimmer. And we're just going to draw our dots, and everybody would draw the same picture, right? But you might connect them and name them differently. You might tie different stories. If you're really making a leap, you might ascribe some meaning to them, but you don't know. You don't know what those dots are. Right? Maybe it's fire shining through a ceiling. There's a Jack Johnson song that's when stars were just the holes to heaven. Yes, that's some people thought that. It's reasonable. How would you know? You got to explore. So the apparent magnitude ranks how bright something appears. Now I want to emphasize, I'm picky about this and people can be sloppy about this word, but bright is just the way it looks. It's not necessarily the way it is. We'll get into this, okay? Just how bright is how it looks to you. Right? If I take a light bulb or a flashlight and I go like this, it's going to look brighter and then it'll look less bright. Remember that. It's one of the two key factors we're going to have here. All right, so apparent magnitude, lowercase m, is the visual ranking of how bright it looks. That's all. It's not a big deal. You got to get used to it. And there's something funny about it too. So let me tell you. The old ways, naked eyes. Brighter versus dimmer. So that's pretty easy. You could say there's dim, there's bright, but then it starts blurring. But you might go, there's first place and second place. So an M of 1 is brighter than an M of 2. Remember that. It's flipped to your common sense. So 1 is brighter than 2. Just think first is better than second. You don't go, woo, I got second place, man. I beat you, you got first place. No, first place wins, right? That's brighter. Now you could tell that there's kind of in between, right? So people wouldn't really do this. Now you go here, that kind of makes sense, right? I got the brightest, and then I got, bright, and it's starting to get kind of dim, and then dimmer, fourth place. But if you really do it, right, you got your picture of the dots, and everybody agrees. You send it by email, of course, thousands of years ago, and you might get a little picture. You go, yeah, I think that this group could be broken into 3: first, second, third, fourth, fifth, and 6th. M is equal to 1, M is equal to 2, 3, 4, 5, 6. Remember, smaller number means it looks brighter. Looks brighter. Not is brighter, it looks brighter. So don't say it is brighter, say it looks or appears brighter, which is a smaller number. You have to pause because you might flip the meaning in your head until you do it a bunch. Now, that's naked eye. And that was a system pretty well set up. But we saw around the time of Da Vinci and getting into there, telescopes started getting developed, and then you start being able to see things that the naked eye can't see because the telescope grabs a lot more light. And then we get better and better telescopes, and we keep making them bigger and bigger and bigger, right? So that's the point, that's the goal. And then you got technology, you got computers, you got things that break down the light. So with modern equipment now, and what we will go ahead and use, even though we're supposed to be ancient shepherds here, we'll break this down and let me fill this in some. So we're going to change this. And I do want, in my class, I want people to remember a few things. See, on this scale, remember that the dimmest you could see was 6. And that's dim, going dimmer. And then this is getting brighter. And then this is the brightest star at night. Right? Well, we can do this for anything. You can do it for sun, you can do it for moon, you can do it for a light bulb. You can rank it. There's a way to do this. Okay. So, on our new modern system, I'm going to extend this. 6 is what we use still, kind of tying it there, to be the dimmest naked eye that the naked eye can see in a dark sky. Go camping or whatever, get away from those lanterns. By the way, you got to turn off all white light for about 15-20 minutes to really dark it out. Don't look at your phone, boom, blast it out. You got to wait another 15-20 minutes. Red light doesn't do that. But the dimmest you're going to see here, now Uranus is here, Uranus is right in here, maybe 5.7 or getting, so people really didn't notice it very much. You might put it on your map, you might not. That's pretty hard, right? Brighter. Now, when you're near a city, you're not going to see this. Why? Because the sky is brighter than the thing you're trying to see. So a city light's going to drown out this. Now this is approximate, don't take it too literally, but if you tell me it's a 6, I'm not going to see it around here, right? Tell me it's a 5, it's like, I don't know, I'll go see, check it out, play with it. You got phone apps, right? I like planets, there's a lot of free phone apps. But 4, I'm going, it's going to not look very bright, but I'll start to see it. 3 is going to look brighter. 2 is brighter. Now notice, even in a dark sky, the human eye cannot detect things that appear less bright than a 6. And it's right in there. We're not worrying about 6.5, or you can get into that more, but you get this idea. And so, what I want to make sure that our video's there, and you can see that, and we're all clear here. Okay, good. So I'm ranking it. All right, I don't want to go there too much. All right. Tell me, what's dimmer than a 6? Yeah, right? Dimmer than a 6 would be an apparent magnitude 7. We often just say magnitude instead of apparent magnitude. Be a little careful with that, but you can't see that with your naked eye. I don't care how dark your sky is. Not human eye, at least. 8? No, can't see that. Hey, that means that no one knew until the invention of telescopes, no one knew that Neptune existed. No one knew. Look up, it's so easy. Just put in the search bar, apparent magnitude of Pluto. I'm not going to make a huge list, but I do expect people to know these. There's an interesting story here. And what's dimmer than a 9? An 8? 9th place, right? And 10th place, and 11th place. There are things really, really dim. You can't see with a naked eye. You got to make bigger and bigger eyeballs called telescopes. And that's how we know about this. But remember that all of this cannot be seen. And by seen, I mean, of course, naked eyes, unaided eyes. So ancestors didn't know anything about that, right? Makeup astrology is like, well, what about Neptune? Now you can throw it in there. It's like, well, what? Okay. What else should you know about this? Well, they get brighter and brighter. Now, here's another misconception that people have, and learned people, fine, but you have different expertises. But a lot of people think that Polaris, the North Star, I'll show you a picture of that, is the brightest star. It's not. It stands alone, so it's in a region where there aren't very many bright stars, or stars that appear bright, right? But Polaris is about a 2. And you go, well, that's bright. So that's the North Star. So do remember that's Polaris. Know that you're getting brighter. 4th place, 3rd place, 2nd place, 1st place. You're a bright star. And then you say, well, what's brighter than 1? Nothing. How do you get better than 1st place? Well, you cheat. Oh. But on this scale, and the way that we do it mathematically, you don't have to know it's a logarithm scale. You take how much light you grab, and you let your computer do the work, and you put it on a logarithm scale. You don't worry about that. But just know this: there is brighter than a 1. It's called 0. In fact, there's decimal places here too. You don't need to worry too much. And brighter than a 0 would then be what? -1. What's a 0? Oh, the star Vega is very close to a 0. And yeah, that's a pretty darn bright star. But guess what? You just saw Sirius, didn't you? Over there in Betelgeuse. What are those? Oh, you can look them up. We'll talk about that real quickly. So in here, what's brighter than a -1? -2. Where's Sirius? Right in about there. Now I'm just going to say negative. So I'm going to say Sirius, the dog star. But again, that's a name. Native Americans saw it too. I'm sure they had a name for it. And the M of Sirius is about -1.5. You might say 1.47, 1.46, whatever. It depends. But that's good enough. So that is the brightest star. And of course, I'm not talking about sun, but that's the brightest star. Now, we keep going, -3, -4, and get in here, and you get some planets. It depends on where they are and how close we are and so on. So know that. And then I'm going to do this, and I'm going to do this rough, and you can look it up and check me. But you can look up. What else is really bright? Let's see if it's in here. What's really bright? Sorry. Here we go. What's really bright? Of course, sun is, right? What else? How about a full moon? Depends on the phase, right? But a full moon is like, and again, just something easy to start with. This is a starter course. So it's like a -13, a full moon. It's bright, right? It's a lot brighter than those dots. And then you go out to about, and this is just an easy way to remember. I know, just you can look it up and be picky, but just a nice, easy way to remember it is double that. That's sun, and that's a full moon. About. And you know how bright that is, right? So bright you don't want to look at it directly. It'll burn the back of your eye, your retina. Okay, so have we got everything I want? Yeah, I think that's pretty good. Now, you might go, oh, you mean sun is twice as bright? I mean, you double it? No, it's not a scale that we call linear. It's a logarithm scale. Anyway, it doesn't work like that. In fact, if you go 1, then you're going 2.5 times brighter. So 1 every shift. So 2.5 times brighter, then multiply times 2.5 again, then times 2.5 again. You don't have to worry about that. So anyway, this is how we do it. And you can talk about it, and you can list it, and you can rank them. And you could do it with your naked eye, but you're not going to do this well. But know this scale. Okay, so I've got a question for you then as we finish off brightness of stars. The other ones will go kind of quickly. My question for you is, what determines, this is going to be important and we're going to use it as we go through the course, what determines how bright a star appears? That is, what determines its apparent magnitude? Think about it. What determines how bright, that is, how small the M is, how bright a star appears depends on what 2 things? I'll give you 2. There's a third too, really, but I'll give you 2. Sorry. Need a camera person. What is it? How bright depends on 2 key things. Let's take a look. Let's take a look at our stars. Bring you back over. And remember this. In the night sky, we just look up and kind of check it out, right? So, let's see. What determines that? Oh, there's Sirius down there at the bottom. Betelgeuse. Those are actually all very bright stars, or bright appearing stars, to be more careful. Let's take a look. And I'm going to turn off the lights. I'm going to turn these on. Okay, ready? I gave you a hint. There's two things. What determines? Remember this. Memorize this. How does this look? Let's take a look. How can I make one look brighter to you than the other? Think about the flashlight. What did I say? You tell me. Now, I've got these pretty close, right? They're pretty close to the same. So they should appear to you pretty close. What happens if I move one farther away? Can you tell? I'm not sure. What happens if I move one closer? Which one looks brighter? Is the M bigger or smaller for this one? The M is smaller. First place, second place. Notice, however, that they're giving off the same amount of light. So distance, clearly. When something gets farther away, it doesn't look as bright. And the M goes up or down? The M goes up because it's less bright. See, it's the reverse. Remember the ranking, remember first place, sixth place, right? So if it's closer, M's going to go down, it's going to appear brighter, even if they're really the same. And so that's the other thing here. You see, and people didn't know, and they wondered, are all stars the same? What are they? They didn't even know that they had any size or shape or anything. You know what they were? How could you? They're glowing dots. But it turns out they are different. There's a range, and we get into that in chapter 11. So, if one gives off less light, and the other gives off, oops, I was dialing the wrong one. All right, fine. If this is giving, they're the same distance from you, but this is giving off more light, we call that the luminosity. We're about to tell you that. You can measure it in watts, how much light energy per second gets to you. But the watts, or the luminosity, capital L, will use that. So if one is giving off more light and the same distance, of course it will look brighter, meaning a smaller M. Little tricky, you gotta play with it. You know, play the song a little bit, go round and round. Now, of course, if the one that's giving off more light gets closer, then it'll certainly look brighter, smaller M. If it's the same distance, it'll look brighter, same M. If it's farther away, it still might look brighter. It just depends on how far away. Right? How far away? Wow, I'd like to know the distance and the luminosity of those stars. Could our ancestors know that for thousands of years of records that they kept? Alexandria, Egypt, etc. Sad story there. Could they know? Could they know? They could know this, though, couldn't they? They could rank the stars. They could draw the pictures, and they would be free to draw the pictures and make up their own stories as they wish, right? Excuse me. As they wish. Tighten that down a little bit. Okay. So we got one. The other one's a little easier, so don't worry. So that's how bright. Very apparent. You go, look, that's brighter than the other. What else can you notice? Well, I just said I wanted to know, I would like to know things like the actual size. And if you look over there, you might say, hey, check this out. I'd like to know the actual size. Can I tell the actual size? Is it just a dot, or is it really, notice that some of them look bigger than the other ones. And if I want to draw brightness, a brighter one I might draw as a bigger. You'll see that on some star charts, right? So that looks bigger. So you wonder, how big are they? They really, with a good telescope, it's just pinpoints of light. But when it comes through our atmosphere, if it's more light, it's going to spread out a bit more. So that looks bigger. But you cannot tell which one's bigger. Partly, what happens, a plane at a distance looks small. Things at a distance look small. You don't know distance either, can you? I want to know, I can't know the distance. I don't know. There are some of these can be closer to us than these. You can't know, and our ancestors could not know for thousands of years. So let's make a list of what you can and can't know, and increase your awareness on some of this stuff. All right. You cannot see with your naked eye. We take measurements and calculations nowadays, but you cannot see with your naked eye the actual star size for thousands of years. Right? Let's make sure you memorize that list. How do you memorize things? Look at it every day, a couple times, just quick. Take you 5 seconds. Quiz yourself. Flashcards, whatever. You cannot see star size. What about distance? You can't see distance. You can't tell. You can't. Now, if you see people and they look smaller, you go there farther away, right? People are kind of in the same range. We talked about that with stars. So the distance away from us. I use the letter D, but whatever, away from us. You could guess, people guess, they try to measure, they try to figure that out. Good luck. Well, what else do I want to know? Remember, the farther away, the dimmer it appears, so the bigger M. I'd like to know that, but also the more light it gives off, the brighter it looks, and the less light, the dimmer it looks. I'd like to know its luminosity. Oops, I told you. You can't tell that. It's not stamped on there. Oh, here's the luminosity of this star. Luminosity. What letter do you want to give it? Sure, capital L. We'll use that. We're going to use that. Okay, so I'm going to tell you something. And you could measure that in units of watts, so if you're kind of familiar with light bulbs, although now you have LED light bulbs, yeah, they're awesome. And this is how much light, and this is in the book, really light energy, but I won't be picky about that. I don't want to say that. It is given off each second by the light bulb, right? Off each second. Now, sun has a luminosity it's a lot. It's a big number. You can look it up. So what we do is compare it with sun. So we use as the symbol of sun a dot and a circle. You'll see why. But a dot, that's a subscript of a dot and a circle. That means sun. And that's how much light sun gives off. Of course, sun looks very bright. Why? It's close. Some stars give off a lot more. Some stars give off less. We'll talk about that. So we'll reference. If it's twice as much, it's 2 of these. 2. If it's half as much, it's half. If it's a third as much, it's a third. I don't know why I write a third, but there it was. All right, cool. So you can't know that. You're going, wow, our ancestors didn't know a lot, did they? No, they didn't. To be honest, they didn't. But they did amazing what they could do. We're totally impressed, but compared to now, forget about it. You also saw them as fixed stars. So they didn't see 2, 3, 4 individual star motion. They didn't see that. we know now they're too far away. Things that far away, light years away, even if they're moving, and they are moving, it won't appear they're moving. As you get farther away from the freeway, the cars look like they're moving more slowly. Planes on the horizon look like they're moving more slowly, and there's an exercise in the text that'll get you to understand that. But they couldn't tell. There are no shooting stars. Not these stars don't shoot. They're far away. We call them meteors. People call them shooting stars, but they aren't. They're streakers. We'll talk about that. Okay, and what else? If you don't know how far away they are from you, one can be closer than the other, then you don't know how far away they are from each other. They look like this on your picture, ... But you don't know this. So you don't know their actual distance the stars are from each other. And that's our list of 5 things, and you could ask more too, but the actual distance stars are, not just from us, but from each other. So what do I write these? Well, I write them because it makes you wonder. And you might wonder, and you could bet that our ancestors wondered. Right? They wondered about this. I can tell how bright one looks compared to the other, and I can rank it first place better than second. 0 is better than first. What'd you get? I got 0. It's better than first. I got -1. But I can't know any of this. So pause. I'm going to start a new video and talk about what you can see, and we'll set this up. Watching the stars, making up patterns, making up stories. Just don't take them literally. Right? I can have a different story than you. Native Americans can have a different story than the Egyptians or the Greeks or the whomever. Chinese, we'll go Incans, name it. Anthropology, right? So let's take a look at this in just a moment, shall we?